Yeah, thanks for the invitation, Sasha and others. And so my talk today is about how rheological inheritance controls segmentation at rifted margins. I'm going to show you some really nice observation and some modeling work that we did for the Labrador Sea. So yeah, so let's just step back a little bit and try to see actually what we mean by inheritance, because it's quite an ambiguous term and it could mean actually different things depending on the context and scale. So in our scale here, we're looking at rifts and rifted margins. We usually actually use inheritance to describe the difference between an ideal layer cake type lithosphere and a real world lithosphere. And that actually put a lot of emphasis on heterogeneities that existed and predated the initiation of rifting. So, and as you've seen with Tom and Chris, is that we have three main types of heterogeneities. We can actually talk about structural heterogeneities, compositional and thermal heterogeneities as well. In my case, I always would like I would like to group those last two into one, which is actually rheological heterogeneities, because composition and thermal state of the crust and lithosphere are usually intimately linked, and they define what we call strong or weak rheology. And obviously inheritance and heterogeneities are important for the obvious reason is the Wilson cycle. And we know that all origins are doomed to fail at some point and collapse. And that actually sets the scene for extensional events which lead to development of rifts, and if successful, then rifted margins and the opening of oceans. So basically, inheritance actually from the previous organic life of the lithosphere can influence the processes by which that damaged lithosphere is stretched, thinned, and ultimately broken up. So this is just like what Chris and Tom mentioned earlier, and basically focusing on structural inheritance. And it nicely showed that inheritance, at crystal scale or crystal weaknesses, they usually get reactivated very early on in the rift process, and depending on their orientation with respect to the stress field, they have influence, they can actually have major influence on fold geometries and the linkage between the different folds and how they grow. And that's really crucial to understand sediment structure relationship in a rift basin, for instance. So in some cases, those inherited weaknesses, they are not restricted to the crust. So, and they sometimes actually they are deeper, and they extend to the lithosphere, to the mantle lithosphere. And that's the case when we have, for example, extinct mid-oceanic ridges, some major transform folds, or even when we talk about zones of subduction and continental collisions. And this is really a nice example from the Labrador and Baffin Bay area over here, where actually you have the Davis Strait between the Labrador Rift and the Baffin Bay Rift, which reactivated this major, which basically reactivated this suture zone here between two major cratons. So we have the North American craton and the Disco craton to the north. And the work that I'm showing here suggests that the inherited weak zone, this inherited weak zone has to extend really deep into the mantle lithosphere if we want to obtain the segmentation that we see between the Labrador Sea and the Baffin Bay. And if we just use a crystal weakness that doesn't extend deep, then we fail actually introducing the geometry that we observe in this area of the Atlantic. And that's actually shows a really interesting aspect, which is that in this case we have a suture zone that's almost 2 billion years old, but that's preserved, and its weakness is preserved through time. And it's that weakness that controls the evolution of rift in this area. So basically it tells us that lithosphere has really long-lasting memory, even though we tend actually to think of lithosphere, because it's governed by viscous flow, we tend to think about it as homogenized over time, over long periods of time. But in here, it's clearly not the case. So like overall, the Atlantic is one of the areas that's actually where structural inheritance have been crucial for the evolution of the rift. And because the Atlantic itself opened on, like after a major tectonic event took place between the Devonian, during the late Paleozoic, between the Devonian and Permian. And those orogenic events involved several successive orogenies that were superimposed in a very tight geographic area. And that circular inheritance is still preserved in the hinterland of the East North American margin that you can see actually on the hinterland. And basically what we see is that the central part of the Atlantic, which was the first to open, reactivated the Appalachians. Then we moved to the segment between the Grand Banks and the Iberia, and that reactivated the Variscans. And then at the end, we moved to the segment between East Greenland and Norway, which reactivated the Caledonites. But if we focus on the area between actually those major oceans that open, we can see actually that we have Labrador Sea, which basically went rogue and propagated across a very old Precambrian structures. So it didn't actually open parallel to those structures, but it just cross-cut them and opened across those major Precambrian structures. And basically it broke off cratons that were assembled during the Greenvillian orogeny. That's almost like 1 billion years ago. So in addition to that segmentation that I mentioned before between the Baffin Bay and Labrador Sea through the Davis Strait, we have huge segmentation occurring within the Labrador Sea itself. And that segmentation can be seen in the rift geometry. And I know that I'm at 10-minute session, so I should be fine. So we have that segmentation actually that's reflected in the geometry of the rift itself. As we move actually in southern parts of the Labrador Sea, if you look at this cross-section C, we have a very wide geometry with exhumed serpentinized mantle. As we move north, we have narrower rift geometry with large amount of volcanics that were in place prior to oceanic accretion. And even that oceanic accretion actually is diachrous across the entire oceanic basin. So we have youngin of the oceanic accretion as we move north. And basically the opening, the lithospheric breakup occur by the end of the late Cretaceous in southern parts, and then it only happened by the mid to late Paleocene in the north. In addition to that, we have also segmentation reflected in the coastal architecture of the margin. And basically what we see is that we have an increased hyperextension towards the south. So overall, what we see is that we have segmentation expressed by different aspects. First, the change in the amount of hyperextension, the change in the magmatic budget during breakup, and also by the change in the amount of in the coastal architecture that we observe. And this segmentation occur across these inherited structures that define a distinct pre-rift segment. And those inherited Precambrian structures that you can see here in black, those actually are rheological boundaries. In fact, if you look at like several geophysical data that's actually have been published, they show that there are changes in the composition, thickness, and thermal structure of the lithosphere across those structural boundaries. And those variation, they can be actually like seen in one data set, which is the surface heat flow. So as we know, surface heat flow is the sum of the basal heat coming from the lithosphere and the rheological heat produced in the crust. And you can see that we have a major increase in surface heat flow as we move southwards. And that basically can be summarized in this diagram here, where we can see that basically in the north, we have a thicker lithosphere, and in the south, we have a thinner lithosphere. In addition to that, what we see is that in south, we have high density underplating that doesn't extend north. It's restricted to the southern domain. So basically, just by imposing a change in the thermal heat flow or the geothermal gradient, that actually has huge implication on the rheology of the lithosphere in the 3D domain. But in addition to that, we think that there is also change in crustal composition, the crustal composition, composition of the lower crust across the different domain, because we think that the lower crust in the north is stronger than the lower crust in the south. And you can see by combining those together, you can see that the rheological profile or the strength profile across different segments actually does change. And you have this thick decoupling domain or ductile domain in the lithosphere that in south that you don't have in the north. And that should have major implication on the processes controlling rifting during the evolution of Labrador Sea. I just should mention actually that I'm going to show you. So next slide is the results of one numerical model, 3D numerical model, and we have done a lot of numerical modeling in 2D and 3D that we recently posted on a preprint that can be accessed, and also the parameter files actually that we used for the modeling can be used to reproduce the work that we've done. And this modeling is done with the open code aspect. So.
You just passed the 11 minutes, so no need to hurry.
Okay, great, thank you. Yeah, okay, so I was going to show you actually one numerical model. I'm not going to go to the details. Basically, the numerical model is constrained by those changes that we see in the geophysical data and that we think actually occur in the lower crust, with having a strong lower crust in the north and weaker lower crust in the south. And then we have this underplating crust that we have only in southern portion of Labrador Sea. So this is 3D numerical model, and what I'm showing here, so this is north, this is south, and you can see actually that we have the crust here. We have a thicker crust in southern parts because we have this underplating that we see here. And then what I'm showing here is a section across the northern part and across the southern part. So this is sliced through the northern segment, and this is a slice through the southern segment. So you can see actually that one of the first things that occur actually is that we have an efficient nicking in the north where we have strong lithosphere and a quick localization of the formation, which leads to continental breakup in the north first, whereas actually in south, because of that decoupling, the nicking actually is delayed, and then you have the hyperextension before actually exhuming the mantle and before actually breaking the lithosphere. But one of the main observations as well is that we have crustal breakup first in the north, which propagates southwards. Once actually the hyperextension is finished in south at that moment to break the crust. But then afterwards, lithospheric breakup occur first south, then north. And that probably has to do with the thickness of lithosphere, because lithosphere is thinner in south than in the north. But we have that diachronous breakup, first crustal breakup in the north, and then lithospheric breakup, which occur first in the south. And if we look actually at snapshots of the model, you can see that we have also like segmentation, structural segmentation in the early phases of rifting, meaning that initially you have some of the strain localized along like specific segments and thus stop actually at the boundary between different segments. So we have an initial structural segmentation as well. And like I mentioned, we have first crustal breakup in the north, which propagates south. And before actually you break the crust in the south, you have major hyperextension going on. And that actually results in what basically we think is similar to what we see in Labrador Sea. And here what I'm showing is two 3D models at 3 different extension velocities. And we see that the extension velocity doesn't change a lot in the geometry in final geometry of the margin. But what we see is that we have increase in hyperextension as we move south. So this is basically just to conclude, and this is going back actually at the work done by Menachel et al. That was published in 2015. And in their work, actually, they basically mentioned that structural inheritance, structural thermal and compositional inheritance have huge impacts on the rift in the initial phases, but then their influence actually weaken as we move into the hyperextension and then into continental breakup. We think that's the case actually for the structural inheritance. It does actually wane as we move actually as the rifts progress. But we think also that the rheological inheritance itself actually is the one that dictates the rifting processes. So its influence on the rift starts from the early phases of rifting, but it does carry on and it persists through the entire rifting phase, and it does influence even the continental breakup at the end. So yeah, that was my last slide. I just wanted to take the opportunity actually to mention something. Probably many of you actually are aware, but this week is Black in Geoscience Week. It's basically something that was initiated and aimed to raise awareness about systemic racism in academia and the lack of diversity in geoscience in particular. So most activities are taking place on social media, mostly on Twitter, but there are also like several live events that are taking place on Zoom and YouTube sessions. So, and with that, I would like to thank you again for listening, and I'm happy to answer any questions if you have any. Thank you.
Thank you. We have time for 1 or 2 questions. Just jump in. Question. Suzanne, is that a question?
Yes, thanks a lot, Mohamed. And as I just wrote in the chat also, thanks a lot for the Black in Geoscience encouragement. I noticed already your jump. Yeah. I'm quite fascinated by your terrain boundaries in a way. So the terrain boundaries are orthogonal to the rift, right? And you put them in your model also as difference in crustal and lithospheric thickness and difference in rheological properties. So does it mean that the opening is mainly orthogonal, so that therefore any terrain boundary that would be there in a different character than just thickness variations, but actually as inherited thrusts and things like that? So, and that therefore they are not seen?
Yeah. So that's something actually, that's a really good point, because that's something that we did on purpose actually when we did the modeling, because I mean, like with this type of model, as you know, I mean, like it's very difficult actually to quantify like one aspect that you want to actually trying to test. So basically, in our models, we don't impose any weaknesses actually along those terrain boundaries. The only thing that happens is the change in the geothermal gradient and composition of the crust. So, but there are like no weaknesses, and what. Initially, when we set up the model, we thought that maybe even without having weaknesses, those zones might actually localize strain and cause issues for the model, but that's not something that we see. I mean, there is no strain localization along those boundaries.
Yeah, but then I guess because you're pulling with a constant velocity at the sites and parallel to the weak zones, but so if you would have, say, a slight transtensional component, or some variation in the extended velocity, then you might get localization on the boundaries, right?
Yeah, we do get issues actually when we try, because one of the things that we try to test is changing the extension rates actually along the margin, and once actually we do that, we start actually having like a lot of strain localization at the boundaries. So the model, and basically, initially it started as strain localization, but the model doesn't like it. So actually, we didn't actually go further with investigating that. But I agree, if we do actually like, we impose some obliquity to the extension, that might have an influence on where strain localized actually.
Mm-hmm. Thanks a lot. I should leave time for other people to ask questions.
Time is kind of up, but let's ask, let's have one more question. Jen Ritter was first, but you asked already a question. That's kind of, you used your question. So Ling, could you ask your question yourself?
Okay, I just wonder how long it takes for complete healing of lithospheric weaknesses and also for crustal weaknesses.
Yeah, that's a really good question. Honestly, I personally don't know. I mean, like I mentioned, like a lot of times, actually, we think that like lithospheric weaknesses, actually, they are healed very quickly because of the mechanical properties of the lithosphere. But then, like I showed, actually, like in some areas, especially like in the Davis Strait, it looks like that suture zone, for instance, it has to be actually, which is like 2 billion year old. It has actually to be there in during rifting actually to cause that segmentation between the Labrador Sea and the Baffin Bay. So yeah, I mean, like, yeah, the short answer is that I personally don't really know. I think for crustal weaknesses, they are actually they can actually like persist for a longer time, but like for the lithospheric ones, I have no idea, to be honest.